Hello, everyone. We'll be talking about pre-stressed concrete, which is chapter 24 in ACI. The ACI structural codes all the structural codes for that matter, are heavy on text but light on visuals. My goal is to take these dense, complex clauses and bridge the gap with simple hand-drawn sketches. You'll be seeing me doing some chicken scratches on the screen. By layering these chicken scratches directly onto the code canvas, I'm trying to transform abstract rules into clear mental images. This visual association makes it much easier for you to recall specific requirements when you are under an exam setting or under pressure. In this video, we are breaking down some essential concepts of pre-stressed concrete, which is chapter 24, to see exactly how theory translates into physical form. We'll be also doing one problem which is comprehensive and should give you a decent idea if you are if you're taking a PE exam or a C breadth setting. Again, in all these videos, I don't get into every little detail in the code. That will make the whole thing very exhaustive. So let's get started. So we are here, ACI 318.14. And then we're talking about chapter 24 here, which is serviceability requirements. Under serviceability requirements is where we have information about pre-stressed concrete flexural members. So the idea would be to find out how these are classified, what kind of permissible stresses, um, how do you pick up the limits from the code. For example, initial compression. What is the limit of initial compression? Compressive stress in the initial stage, that is after release. Um, all that. Anyway, we'll be finding out some bunch of limits. Let's get into page number 409. As you see, this is about permissible stresses in concrete flexural members. Very short section, but then there are a few tables and we need to understand a little bit of a story here, right? So firstly, what is a pre-stressed member? As the name suggests, the member is pre-stressed before it even gets into the site. So what they do is imagine a tub like that, and then imagine putting reinforcement like this, and then stretch the reinforcement, right? Create a tension in the reinforcement, and hold it like that. How do you do that? That's all a technical detail. I mean, there'll be a stress jack, and there'll be one jack on this side. There'll be another jack on this side. But just for imagine that you are in a position to stretch the tension reinforcement. You hold it like that, and then you come back and cast concrete here, right? So this is just concrete, correct? And then you will let the concrete harden for probably, let's say, 2 days, whatever. So after it has hardened, maybe the initial FC prime value is like 4,500 psi, right? So once that is done, what you do is come here and then start to cut the wires, right? Once you cut the wires, the wire will want to go back. So in the process, it is going to apply a compressive force on this section. So let's say here is the neutral axis, but then there is a compressive force. So you, on a section, typical section, it is like this. You have your reinforcement here. Oops, let's say I draw it like this. Let's say you have a section like that, and then here is the neutral axis, but then this is the beam depth. So that's the depth of the beam. That's the beam. This is the neutral axis. Here is where the reinforcement was initially was under tension, and you cut it, so it is going to apply a compressive force. So there is an initial, let's call it a pre-stress force, which is being applied. and that is being applied at an eccentricity, obviously, meaning that is from here to here is your eccentricity value, right? So the advantage with this is you are in a position to, I mean, the beam initially has compression at the bottom and tension at the top, because it is creating a moment like this. This is P, that is E, so it's a creating moment like this. So it's going to compress this layer and then stretch the top layer. Now you come back and then you add your loads. Then those loads are going to those loads will produce a moment like this. So they are going to reduce this compression down, because when a moment like this from dead load or from live load is gonna cause tension at the bottom. So it is gonna eat away the portion of the tension is gonna go away to nullify this compression here, right? And what you're left with is a slight tension instead of having a lot of tension under at the bottom fiber, right? So that's a basic of prestressed concrete. um, the basics about why we want to pre-stress our beam. But let's see what the code has to say, right? So this section here, there's a small classification. So they're trying to classify your pre-stressed concrete, and that's pretty important. So obviously there's a small table here, and you need to whenever you have a table, you need to understand whether you fall here, or fall there, right? So how do I know that? That depends upon the tensile stress in the bottom of the concrete. For example, you have a beam here, and then it is, let's say you're loading it. Now this tensile stress is not in every condition. It has to be at service loads. If you read this, pre-stressed fracture member shall be classified either as U or T or C in accordance with this following table, based on external fiber stress in tension in the pre-compression pre-compressed tension zone, right? So let's say you have a beam like that, and you will have to under service loads. You have service loads. Under service loads, you need to find out what your tension is. Maybe tension might happen here. Maybe tension is happening at the top fiber because of all the initial pre-stress. So you'll have to find the external fiber tensile stress, and then compare that stress with the rupture modulus of concrete, or the tensile strength of unreinforced concrete. And that's why you will see this term being compared with a term called 0.75 root FC prime, and this is the tensile strength of concrete with no reinforcement in it, right? Or modulus of rupture of concrete. So we compare. So if this FT value is much less than the stress in the external fiber during induced due to service loads is much less than or equal to rupture modulus, that means there is not enough tensile load to crack the beam. So that's why it comes under the uncracked classification here. If that stress is between 7.5, meaning it exceeds the rupture modulus, but it is less than 12 prime 12 square root of FC prime, then you are in a transition zone, meaning that the cracks are expected, but those cracks are expected to close if you take off the service load. Meaning one day, let us say the service load is gone. It's a holiday bridge, or the bridge is closed and there are no cars on the bridge. Then the crack is expected to close, right? It will close only if it is between these two values there. So those sections are called tension controlled. Transition between uncracked and cracked. Those fall under the transition region, because your FT is between these two values here. And then you have another classification which is cracked, wherein your FT, the extreme tensile stress when the beam is subjected to service loads. That's pretty important here. The service loads is greater than 12 root FC prime. So in this case, cracks will be there, and then you need extra measures, crack control measures, and all that. So the uh, the detailing and the serviceability requirements are slightly different, right? So usually, if it's a watertight structure, those are the structures in which you prefer your U, right, wherein no cracking is allowed. And then in structures like long span bridges, wherein some cracking is okay, and stuff under heavy load, then transition T is also allowed, right? Okay, so let's go to the, so now we know how to classify the section based on FT. Again, based on your FT value, you will be either U, you will be either T, or you will be either C. Usually this information is given in the exam, and based on that you need to pick up some of your limits, right? All right, so let's go to the next section here. So here is a table. If you are a U, if you are a T, if you are a C, then how do you calculate your gross section? You go to that to calculate your gross section properties. How do I get my allowable stresses? You go there to get your allowable stresses. I mean allowable stress at transfer. I will talk about at transfer and all that. But here is a table which gives you, if you are a U category, then you need to pick up your information from all these sections. For example, if you want to find out what is your maximum tensile stress limit at service load, then that value is here, right? Is there a special requirement for crack control UT? No. Whereas if you are here, then you need to, there is special requirement that you need to follow. Okay. So now let's talk about, before we get into the next sections, let's talk about um, these words here. For example, what does a transfer mean, right? So yes, this is giving you, helping us with permissible stress in concrete. But what does a transfer of pre-stress mean? Okay, we'll be focusing on words like that. We'll also try to find out what concrete compressive stress immediately after transfer of pre-stress. What does that mean, right? So we'll try to talk about those, and then come back and then do an example wherein we'll pick up all these values. Same thing here. Concrete tensile stress immediately after transfer of pre-stress. This is 10. What is the limit? I mean, how do you find the limiting tensile stress value? Immediately after the transfer of pre-stress. What does that mean? Correct. And we'll also find out what these limits are, and why are there different limits at service loads. Right. So to understand that, we need to understand a small story here. For example, uh, let us say you cast your concrete beam. That's a concrete beam. Here is the reinforcement, right? So this is the reinforcement which you initially have it under tension, and you cast the concrete. The concrete gets hardened. This is all concrete, right? And it becomes a concrete beam, right? So that's your concrete there, right? And it hardens and it becomes like that. This is aggregate, right? Um, Now you come back and then cut the reinforcement there, and the reinforcement, because you can cut the reinforcement so that you can use the beam. Now that you cut the reinforcement, the tension will get translated. I mean, the reinforcement is wanting to retract, and it is applying a compressive force here. Meaning, if this is the section of the beam, here is the neutral axis, right? That is the neutral axis. Now you have a compressive force acting at a certain eccentricity E. So that eccentricity is from here to here. That force is acting at that eccentricity, right? So so once you cut, that scenario is called at release. So once we release that, at that point in time, the only thing acting on the beam is um, the self weight, right? So W self weight is acting on the beam, and you also have your force due to force due to the compression. Let us say you pull the steel strands to a stress some Fs initial, right? And then you know the area of your strands. Uh, so once you multiply that, that is the P initial that I am talking about. That the P initial which is trying to press the beam, and then there is a self weight. So at this stage, if you try to find out the compressive and tensile stresses, um, you will go back to your basic mechanics, wherein the compressive force, I can replace this diagram firstly with a P acting at the neutral axis and a clockwise moment, P times of E, P times Pi initial times of E acting like that. And then there is self weight, which is causing a anti-clockwise moment. So this is the moment caused because of self weight. Let us say I'm using loose terminology here, but then loose notation here, but then the idea is to just convey the message. So this Pi again, what did I do here between here and here? What I did was I replaced this particular force, which was at a certain eccentricity, with a force acting at the CG of the section, which in this case is the neutral axis of the beam, that is d by 2. And I replaced the P times of E moment is this P times E moment, plus the self weight is causing MW, MSW, right? So that moment can be, if the span, let us say this is simply supported and the span is L, then, and you know the self weight as W LB per feet, something like that. Then MSW is nothing but your W self weight, L of the span of the beam, square by 8, right? So that's the moment due to self weight again. This is the PE is the moment due to the initial stress, and PI is the stress caused by reinforcement trying to compress the section, right? So, so what you do is you take a section there and then find out because of this compression, because of this PI, the stress induced is uniform across the section because that PI is supposed to be acting at the center. So the compressive stress is just PI by A gross, right? Then you add the effect of this PE. This PE is a clockwise movement and it is trying to compress the bottom layer and stretch the top layer. So compressive force here, tension force here. Um, if you can follow the same notation like that, and this is your tensile force. So you find out this stress, which is due to your Pi times of E, that is the moment. You divide that with the section modulus to get your stress, right? So this is the moment, this is the section modulus. You get to, and you find that out to calculate your tension stress, compression stress. Now to this, there is another moment. The effect of this moment is it is gonna, because this is anti-clockwise and it is trying to bend the beam. It is trying to bend the beam like that. So you have tension at the bottom, compression at the top. So this one is tension at the bottom, compression at the top. Again, I am following the same um, tension at the bottom, arrows on this side, compression, arrows on that side. So this is compression. How do you find that stress? You take your MSW, which is the WS L square by 8 divided by the section modulus to get that stress, right? So at the bottom, so in this case, top and bottom fibers are subject to compression. In this case, this moment is causing the top to be under tension, bottom to be under compression. This moment, because of the dead load, is self weight, is trying to cause compression on the top and tension on the bottom, right? So that is called at release. So for this scenario, once you find these stresses, so the final stress, let us say at top, at top fiber. So the final stress at top fiber is Pi by Ag, because this is compression, plus or I should say minus pi e by z, because why minus? Because this is tension at the top fiber. Here is compression, so plus MSW, that is moment due to self-weight by the section modulus, right? So you compute this stress. Well, after you compute this stress, you need to compare it with a compression stress limit, right? And that limit depends upon if you are in the initial stage, or if meaning after initial stage, after you cast it and then let it harden, right? Or if you're talking about a final stage wherein the concrete has hardened, gained its final F prime C. For example, in this case, after so many days, it can have a FCI of FCI dash of 4500 psi. But after some time, it's going to gain its final strength. So and that will be FC prime, which will be 6000, close to 6000 psi, right? So stress limits that we need to use, in short, during initial stage are different from stress limits that you're going to use during final stage, right? How do you calculate your stress values for initial stage? This entire slide here is only for initial stage, meaning after release, after you cut, do that birthday celebration by cutting the ribbon, right? So once you cut your compression steel, immediately after that, the reinforcement is going to trying to compress the beam at the bottom, and going to create a slight tension on the top, and um, that in conjunction with the self weight is going to create a final stress value which has three components. One is due to the pure compression, one is due to the PE moment, one is due to the moment about the self weight, I mean moment caused by the self weight, right? Now let's talk about the um, final stage, which will be split into two categories again. For example, let's say you have your beam ready now. You have already cut the ribbon, right? The stress is already, and this is ready to be installed. So you pull it here and then support it on, let's say, two supports, right? Now the strength of FC prime, the compressive strength of concrete has reached its final value. Let's say that is 6000 psi in this case, right? um, and you have already installed some dead load. Maybe there is another slab sitting on this particular beam, so you have your UDL because of the dead load, which is superimposed, plus you also have UDL, that is another dead load, but this is self weight, right? So now you see new loads being introduced, correct? So at this stage, this is a final stage, but then this is a serviceability service. This is a stage wherein you are still not allowing your live load, right? You are not allowing your cars and other things on the beam. So you only have dead load and you have SW, correct? So that scenario in the code is called um, pre-stress. I mean, you have your pre-stress effects. So you have your pre-stress and you have sustained loads. So sustained loads are W due to the dead, plus that means maybe you have installed a concrete slab on it, plus W due to the self weight of the beam. So at this stage, again, the story is the same. You have your cross section like that, and let us say this is the neutral axis. You have your P final, because now the reinforcement has relaxed a little bit, and it has its the final stress in the reinforcement. It's not the same value that you initially stretched it for. Let's say you stretched it for 175 psi. Now after some time, it's going to go back and it will become 160 psi. Let's say. So you have your you still have your compression, but it's not fully lost. But then there will be some losses, long-term losses, right? So those are called long-term losses. So your PF is acting obviously at an eccentricity. Now you have moment due to the dead load, which is trying to This is the beam. It's trying to bend the beam like that, correct? So it's a anti-clock moment due to M dead, and you also have a moment due to the same moment that you already had due to self weight, correct? So you can club these two and call it, okay, my total dead load moment, or dead load, meaning the superimposed dead load plus the self weight is total dead load, MD total, let's say total. And how do and then you can how do you calculate that moment? You have the UDL MD WD total, which is a sum of your WD and which is a sum of your W self weight, right? And simply supported, let's say span L W T total L square by 8. You have your moment there, right? Now you need to calculate the stresses. So let's say so this load will cause, so this entire thing can be assumed as can be simplified just based on method of superposition. Let's say this is the neutral axis. I can replace this force as acting there, and I can add a moment which is acting clockwise. This is due to pre-stress final, right? Not initial. This is a pre-stress final force. Plus you have your moment due to uh, your total dead load, right? So what I can do is I can calculate on a section. This PF is going to cause a compression, uniform compression of PF times A gross, right? And to that I add the effect of the moment. The moment is going to cause compression at the bottom and tension at the top. I'm talking about this moment here, which is the PE moment, and so this is tension at the top, and you can calculate this by taking your M moment caused by your final pre-stress divided by Z, right? So this is tension, this is compression, right? So here you have compression. Here also there is compression at top and compression on bottom. Then to that you add your moment caused because of your dead load, obviously, because the total dead load, which is the dead load, and the self weight is going to cause tension at the bottom, compression on the top. So it will be a diagram like compression on the top, tension on the bottom. So this is your tension on the bottom, then this is your compression on the compression on the top, correct? And how do you calculate that stress? That will be from your moment due to dead load divided by the section modulus, right? So based on this, you can calculate your stress at either at the top fiber or at the bottom fiber. Now we'll just do it for the sake of it. We'll do it at the bottom fiber. The total stress at the bottom fiber at the final stage, let's say. I'm again using all the notation loosely, but you understand the idea is to just convey the message. So the total stress at the final stage is your PF by AG. This is positive compression. I'm talking about the stress at the bottom, that is here, here, here. I'm adding all those values. Plus you add the stress due to your MPF by Z, which is also compression, and then this fellow is tension here. So you add your MDT, that moment, by the section modulus, that is your stress, and then because we did a minus because it is a tension. So you compute that quantity, and then I'll show you how you can find out the, if let's say this whole thing is compression, then we need to pick up the compression limit of concrete subjected to service loads, uh, and especially due to permanent loads, meaning sustained and self weight, right? So now let's move to the third category, which is you have your sustained loads, um, or you have your pre-stress loads, plus you have your you have all other loads, right? So that means you have loads due to pre-stress, you have loads due to your superimposed dead load, you have loads due to your self weight, and you have also loads due to live load. So this is again serviceability condition, and wherein you have not just dead end service, but you also have your live load, right? So that means your beam is ready. You did the rubber cutting, so there is compression there, and you installed a deck slab already on it, so that is causing WD superimposed dead load. The beam is already concrete and it has self weight, that is causing self weight. Plus you are allowing a vehicle to pass. Let's say you have opened the bridge for traffic, right? So now you have live load component as well. So when that happens, uh, again you can simplify it. There is a compressive stress in steel. Steel has already relaxed a little bit, so it has a final stress. Here is the neutral axis. You have your dead load moment acting like that. You have your self weight moment acting like that, and you have your live load moment acting like that. So so this is moment due to, or all the sum of all these three is moment due to dead load and live load, right? So three moments: moment due to dead load, moment due to service self weight, moment due to live load. All are acting like that, correct? Um, and then there is a PE moment which is acting in the opposite moment, which is the P final times your eccentricity. How did we get this? Again, this entire thing can be replaced as if the compressive force is acting at the center, and you have your three moments, right? And you have your P times of eccentricity acting in this direction. This moment is due to, let us say, moment due to dead load, moment due to self weight, moment due to live load. This is moment due to P final, right? So which is nothing but P times of E. So in this case again, the now you have a beam like that. These three are uniformly distributed loads, let us say, right? So you can call this moment due to all other loads, all loads, right? So moment due to all loads, you there is this is the length. So W, or let's call this um, W dead plus W self weight plus WL, right? So this is W total. W total times L square by 8 is your uh, maximum positive bending moment there at mid span, right? So what you do to calculate the stresses, again you start with the basics. The P is going to the PF is going to compress the section uniformly, because I'm assuming that the PF is acting at the centroid of the section. So this value is a compression. Even at the bottom fiber it is a compression, and the compression value is equal to PF by A gross, right? So to this you add the effect of MD, MS, ML all acting in the same direction. So um, or let us finish the P times of E, which is let us take care of this thing here, right? So that one is compressing, is creating a compressive force at the bottom, tension force at the top. Why is it that? Because you have your beam like this, and then the force is at an eccentricity, right? So it is a causing a moment like that. When you do that, you create compression at the bottom, you create tension at the top. So I'm talking about the PE moment. So this PF, P final into E. Why is this final? This is final because the stress in the bar is relaxed. It is not the same value that you and your friend pulled the uh, reinforcement member, right? You stretch the reinforcement to cause tension. So after that fact, it has relaxed a little bit, and you have slightly lesser stress. So your PF value, so we are talking about the moment, which is PF acting at an eccentricity. So that is causing a tension on the top, compression on the bottom. Compression is like that, tension is like that. The value is, you find out the moment caused by that PE moment, which is P final times E. You divide it by the section modulus, right? To that you add the effect of the total dead load. The total dead load is causing a compression at the bottom. Because of this, the beam is going to deflect like that, causing a tension at the bottom, compression at the top. So you have tension at the bottom, compression at the top. So that is like this: compression at the top, tension at the bottom, tension, 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 right? Mm. And how do you find that stress value? You find that stress value by calculating this moment. So M dead total divided by your section modulus, correct? Now you can, once you have this, you can use method of superposition to calculate your final stress. Let us say like final stress at the top fiber final, right? And that value is nothing but PF by AG. We're talking about the top fiber, so that is compression. This is compression, right? Minus PF into E by section modulus. This is tension, that's why it is a minus, right? And then you have your plus M dead by section modulus, and that is a compression, correct? Now, after you do this, to qualify your beam, you need to figure out what is the compression limit, what is the tension limit, right? So the rest of the chapter, rest of the details that we'll be talking about is about that. So let's go back. Let's start from here, right? So if you see this one here, this is the compressive stress, limits on the compressive stress, permissible compressive stress after the transfer of pre-stress, meaning immediately after you cut the ribbon. Once you cut the ribbon, you're not allowing live load yet. You just cut the ribbon. Then what is the, and once you cut the ribbon, obviously the reinforcement wants to retract, so it is causing a moment, so it's causing a compression at the bottom, it's causing a tension at the top, right? So what is the we talked about how you can calculate the compressive stress value, and you compare that with your tension. Sorry, you compare that with your limit. Now the limit, if you are calculating your bending moment at mid span, or sorry, at the simply supported ends, then you will have to use this value, 0.7 times FCI. But if you are calculating, if the stress that you are computing is somewhere else, let us say in the mid span, where in the maximum bending moment is going to happen in simply supported case with UDL, then you are going to compare that value with 0.6 times of FCI prime. So you have to notice that here you have not FC but FCI prime, because the concrete might still be under 400 psi during this initial phase. After when it goes to a final phase, it gets hardened, it reaches its final strength, and that might be FC prime is like 6,000 psi or something like that, right? So here, when you're doing this at transfer of pre-stress, you're not using this value. You'll have to use that particular value. So moving on to the next section. So here is another table, and this gives us the tensile stress limits. Remember, once you cut, initially do the rubber cutting, there is a compression reinforcement. You stretched it, but then the reinforcement was to go back, and it is compressing the section, so it is going to cause a compression here and a tension on the top fiber, let us say. How do you find out? We talked about how to calculate the stress on the top fiber, but what do we compare it with? We compare it with either this value or this value. And now in a table, again, you need to find out if you are here or if you are here. If you are here, if you are talking about the stress value at the ends of a simply supported beam. Elsewhere, you are talking about this compression. So 3 root FC prime is what you need to compare your tensile stress with, right? Notice that this value is less than your tensile strength FC 700 roof FC prime, right? So now moving on to the next section, we have this one here. This is talking about permissible stress, permissible concrete compressive stress at service loads. So now we have two scenarios, and again you have two scenarios here in this table. And the code language explicitly says pre-stress plus sustained loads. And this is the condition that I was talking about, wherein you did the rubber cutting, you have your um, steel wanting to retract and cause a compression. plus you have already supported it, right? You have not, maybe you have also installed a concrete slab on this beam. So the UDL, there is a UDL because of the dead load, plus there is a UDL because of your self weight. So these two clubbed together are called sustained loads, right? So pre-stress plus stress plus sustained loads. Pre-stress is this compression, this compressive force that is being induced by the reinforcement, and then the sustained load is caused because of your dead load and self weight of the concrete. Now, when that is the scenario, then you use a compressive limit of 0.45 FC prime. Um, The next row here in this particular table is pre-stress plus total load, and in the total load scenario is divided into three categories. One is load caused by your dead load. You have that means you have already installed a slab on the pre-stressed girder, and you have the self weight of the girder acting obviously, and then you have opened the bridge for traffic, so you have a live load component. So the UDL in this particular case is due to dead load, due to self weight, and also due to live load. Um, and that is called pre-stress plus total load. So in this scenario, you will have to check your limits against using this particular row here, which is 0.6 FC prime and not 0.45 FC dash. Moving on to the next section, we'll go to the tension side now. Okay, so we covered the compressive stress. We covered the uh, compressive stress at limits at service loads. We covered the tensile stress immediately after transfer, and we also covered compressive stress limits immediately after transfer of pre-stress. So in the next session, we'll probably do a problem on this just to solidify the concepts, and we'll take an example problem. We'll take a small beam and subject it to dead load, self weight, and live load, and then try to find out the stresses firstly, and then we'll also try to find out. Uh, we'll also try to see how that compares with other things. Thank you.